me just give you the definition of concavity of a function for one variable. Okay, so let me give you some graph. Okay, and then I'll tell you all these graphs of functions are of in one category, belongs to one category, and we call them concave functions. And then I'll tell you what kind of property is true about all these graphs. Okay, and that property defines concavity. Is that okay? Fine. Okay, so suppose you have a graph like this. Okay, fine. Or you have a graph like this. Okay, or you have a graph like this. Okay, so all these are kind of three different functions, and all these three functions belongs to the same category. We call them concave functions. Okay, you can also have linear functions like this. They also belong to the category of concave functions. Okay, and you can also have piecewise linear functions of this type. Okay, where let's say function is first increasing at this rate. Okay, and then the rate falls a little bit. Okay, and then it is increasing at a smaller rate. Okay, but all these functions that you see in this graph, we will call them concave functions. Okay, even it can also be like downward sloping. It doesn't necessarily have to be upward sloping, it can also be downward sloping. Okay, and it can also be like this. Okay, so all these functions have one property in common. Okay, and first of all, I'll just give you the that particular property in graph, and then I'll just give you the formally what that property means. Okay, so what do you think if I just pick a secant line? Okay, so what is a secant? So if you take the graph of a function, okay, and pick 2 points, any 2 points on the graph of a function, if you connect those 2 points, okay, by a line, okay, that's basically the secant line on the graph. So if I take a secant line like this, what can you say about that secant line? Let me take this one first. Okay, so if I draw what is common across all these graphs, what can you say about the secant line? It's below the graph, and that's exactly the definition of concavity. So no matter what 2 points you want to pick, the line connecting on the graph, okay, no matter what 2 points on the graph you pick, the line connecting them either lies on the graph or below the graph. It's possible it lies on the graph, that's allowed, but no part of it should lie above the graph. Okay, so no matter what 2 points you're going to pick on the graph of the function, and you connect them by a straight line, okay, then that line segment, okay, that you get, no part of that line segment should lie above the graph. Then we say that the function is concave. Yes. On the graph, we are allowed. We are allowing for the secant line to lie on the graph, but we are not allowed to have any part of the secant line lying above the graph. Is that okay? Yes. Yeah, sure. So in all these cases, you can see that no matter what 2 points you will pick, so like for example, in this case, no part of the line lies above the graph. If I pick these 2 points in this particular situation, no part lies above the graph. If I pick these 2 points, no part lies above the graph. So no part of the line lies above the graph. You can see that it's always either on the graph or below the graph, no matter what pair of points I pick on any of these functions. Do you agree? Yes or no? So all these functions have this property. Okay, so this is precisely what concavity is. Have you all understood this? Okay, yes. Okay, so so you have a graph of a function. Okay, when do we say that this particular function is concave? We say that this particular function is concave if you pick any 2 points on its graph. Okay, and you consider a line segment connecting those 2 points on the graph. If no part of that line segment connecting those 2 points lies above the graph, then we say that the function is concave. So this should be true for any pair of points. Okay, so notice that no matter what pair of points I pick, I'll always get the line segment connecting those 2 points on the graph, either on the graph or below the graph. No part of the line segment lies above the graph. Is that clear? So all these functions are concave functions. Have you all understood this? Any questions about this? Okay, fine. This is precisely the definition of concavity, not just for one variable functions, but also for multivariable functions. Okay, I'll give you the formal definition when I'll do the multivariable, counterpart of it. But this is exactly what it means, concavity. Okay, so you pick any 2 points, no part of the line segment lies above the graph. Is that clear? So let me give you, examples of functions that are not concave. Okay, so these are all concave functions. We see that these particular functions satisfy this particular property. Yes. I mean, is it bad? I thought I'm good at drawing. Okay. Okay. Anyways, so you want to see in Desmos? I'll show you in Desmos. Okay. So what I'll do is I'll give you some functions. Now that you know the definition, okay, I'll give you the graph in Desmos, and you will have to tell me whether it is concave or not. Okay. Fine. Okay. Is this concave? Yes, it is. Very good. What about this one? Is this concave? Yes. Very good. Fine. So, do you want more examples? Yes. Okay. Fine. Hmm. What about this one? It is not. Is that fine? You can see that if you pick 2 points here, okay, it's not going to be entirely below the graph. Okay, so it's okay. So I haven't defined what convex is, but let me just tell you what convex is now that you have asked this. So the convexity is basically just the opposite property. Okay, so we say that the function is convex if we take any 2 points in the graph of the function. Okay, the line segment connecting them should lie either on the graph or above the graph, and no part of that line segment should lie below the graph. Okay, so that's what convexity is. So obviously we have functions that are both concave and convex. For example, linear functions, fx equal to x is both concave and convex because I'm allowing for the function to lie, I'm allowing for the line segment to lie on the graph in both cases, and therefore both linear functions are both concave and convex. Is that fine? Yes. Any questions? Okay, great. What about? No, I haven't said that. I've said linear functions are both concave and convex. No, let's see. Now that we, we know both concavity and convexity, we can check for both in this case. Okay. Now, carefully look at this. What do you think? Is this concave? Is this concave? Why not? Because if I pick, let's say, these 2 points, the line segment lies above the graph. Now, let me ask you, is this convex? No, it's not convex either, because if I pick these 2 points, the line segment lies below the graph. So it's neither concave nor convex. Okay, so let me again give you the definition. So what is the definition? Definition says, when do we say that the function is concave? We say that a function is concave if no matter what pair of points you pick on the graph, the line segment connecting those 2 pair of points should lie either on the graph or below the graph, and no part of it should lie above the graph. That's what concavity is. So every word is important. Okay, no matter what pair of points you pick, this property should be true. Okay, so in this case it's not concave because I can find a pair of points for which that property is not true. You know, if I take these 2 points for example, you know, the line segment connecting them lies above the graph. So basically it is not concave. Similarly, it is not convex, because what is the property for convexity? We say that a particular function is convex if no matter what pair of points we are going to pick on the graph, the line segment connecting them either lies on the graph or above the graph. No part of it should lie below the graph. Okay, so is that true about this case? No, because we can find a pair of points here, you know, such that if I connect those 2 pair of points on the graph, the line segment lies below the graph. So that means this particular function is not convex. So basically it is neither concave nor convex. So we have seen functions which are neither concave nor convex. We have seen functions that are only concave, not convex. Okay, we have also seen functions that are both concave and convex. Similarly, there are also functions which are convex but not concave. You know, let's say for example, you know, x square is convex and minus x square is concave. X square is convex but not concave. Minus x square is concave but not convex. Okay, you want to see that?
The straight line would be convex and concave.
Both, yes. Okay, x square, look at this x square. All linear functions are both concave and convex. Okay, so you can see that x square is convex, and what about minus x square? It's concave but not convex. Okay, minus x square is concave but not convex. X square is convex but not concave. Is that fine? In fact, this is a property which holds in general, that whenever a function is concave, you multiply it by -1, you'll get a convex function. Yes. Circle is not a function because it's going to fail the vertical line test, right? Yes. Anything else? Yes. Any other questions? No? Is this clear? Concave, convex? Yes.
What about like a wave function? Would that be either concave or convex?
So you mean sine function? Okay. Okay, let's just check that. So we already know sine looks like this. What can you say about sine function? You can answer this very easily. What do you mean both? Both concave, convex? Neither concave nor convex. It's not both concave and convex. It's neither concave nor convex. Okay, just go back to the definition. Definition says that, you know, no matter what pair of points you pick on the graph, the line, no part of the line segment should lie above the graph. You know, then we say that the particular function is concave. Now, can we say that this particular property holds for this particular function? No, because if I pick these 2 points, for example, you know, on the graph, then line segment connecting them lies above the graph. So this particular function is not concave. Okay, and if I pick these 2 points, for example, on the graph, the line segment connecting them lies below the graph. So this is not convex. So this is neither concave nor convex. Makes sense? Yes. Okay, so basically a good question. So the question says that if I restrict my function to, let's say, a particular interval, For example, what we can do is we can restrict it from, let's say, 0 to yeah, pi by 2, or so then yes, so it's possible that if you restrict your function to a particular interval and you are only asked whether this particular function is concave on that interval, then you don't have to check for the entire graph. You just have to look at only in that interval if that particular function satisfies this particular property or not. Is that fine? Make sense? Any questions? So it's the same thing, right? I mean, if I'll ask you whether this particular function is increasing in this interval or not, so you just have to check in that particular interval if the function is increasing or not. If I'll ask you, is this particular function concave in this particular interval or not, then you just have to check in that particular interval if the function is concave or not. Okay, so concavity, as we have just seen, there is a way to know whether the particular function is concave or not by looking at the second derivative. Okay, provided the function is twice differentiable. Is that okay? If it is not twice differentiable, then you may have to plot it, or you may have to use some other methods to figure out whether the function is concave or not. But basically plotting helps, because then all that you have to do is just check if the line segment connecting them lies, because that's a precise definition. Okay, that doesn't we don't impose any restriction that the function has to be twice differentiable or not. That's a precise definition of concavity. But if, let's say, you get a function which is twice differentiable, then then it's actually very, very simple, because all that you do is just have to check if the second derivative is negative or not. Yes or no? Because if you just look at all these functions, if I just take this particular function, for example, it has this property that it's derivative. So if I draw the tangents, what can you say about the slope of these tangents? It's not in absolute terms, but in actual terms, slope of these tangents, it's falling, right? It's falling. The slope of the tangents is falling. Here it was close to 0, and then it became, let's say, minus half, then it's minus 1. So these numbers are falling, right? And negative numbers, so it's fall, right? Minus 1 is smaller than minus half, minus 2 is smaller than minus 1, and so on and so forth. Yes.
Are all strictly increasing functions concave?
Are all strictly increasing functions concave? Okay. What do you think? What do you think? Anybody? Are all strictly increasing functions concave? Any answers? No.
Convex, like you have like an exponential function.
So you're saying all strictly increasing functions are convex?
No, I'm just saying that you can't tell.
Yeah, so just by looking at whether the function is strictly increasing or not, we cannot tell whether the function is convex or concave. The reason is because if you have a strictly increasing function, let's consider a strictly increasing function like this. Do you agree that, okay, just a minute. Do you agree this is strictly increasing? It's concave. Do you agree this is also strictly increasing and it's convex? Do you agree this is also strictly increasing? It's neither concave nor convex. So anything can happen. Is that fine?
Yeah.
Okay. 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 So if you have if you have a twice differentiable function, okay, then all these tangents, if you see as x increases, okay, the slope of the tangent is falling. Okay, in absolute terms it is rising, I agree, but in actual value of the slope is falling, right? Because it was close to 0 here, then it became close to -1, then probably -2 or whatever. Okay, and then it's just falling like this. Is that fine? Okay, so this is a property of concave functions. You know, whenever the derivative of a particular function is differentiable, then we can differentiate the derivative of the function to get the second derivative of the function and check if the second derivative is negative or not. If the second derivative is negative everywhere, then we get the shape. Yes or no? We get the concavity. Okay, so this is like a test for concavity, the second derivative test for concavity. This doesn't mean that, as I've told you, there is a possibility that you may have other functions which are not twice differentiable, but they are still concave, because the actual definition of concavity is, you know, if you take any 2 points on the graph, the line segment connecting them lies either on the graph or below the graph. Okay, that's the precise definition, but this is just a test. If the function happens to be twice differentiable, then you can use this test. Is that clear? Okay, like for example, this one, you know, is a concave function which is not twice differentiable. In fact, not even differentiable. It is a concave function. Yes or no? Is that clear to everyone? Understood? All of you? Any questions about concavity, convexity? Yes. Yeah. Okay. So anybody knows answer to this question? It will be, so you're, according to you, it's both convex.
Because if we pick like random points with the same light segment, the same interval, then in that case it's both concave and convex. But if we pick when x is equal to 1 and x is equal to 0 and we make that line, I have no idea.
Okay, fine. Okay, anybody? So let me ask, anybody has any answer for this? Is this function concave or convex, or both, or neither? Yes. Okay. Can be above also. Okay. How about this? What about this one? So if I take these 2 points, what do you think? Part of it lies above, part of it lies below. So it's neither concave nor convex. That's it. Bolo. Because if you connect these 2 points, this line is neither below the graph nor above the graph. It's neither entirely below the graph nor entirely above the graph. Part of it lies above the graph. You know, so if you see from this point to this point, it lies above the graph. From this point to this point, you know, it lies below the graph. Since part of it lies above the graph, we cannot say it is a we will say that it is not a concave function. Since part of it lies below the graph, so we'll say that it is not a convex function. So it is neither concave nor convex. Yes. Yes.
So what if the function is discontinuous?
It is discontinuous.
No, like in general.
Okay, so that's interesting. Okay, so what about this? So if suppose we have a, what is the connection between concavity and continuity? That's what you're asking, right? In general. Okay. Yeah. What do you think? Can we say that? Okay, so you think that there are possibilities where we have discontinuous functions which are concave? So can you think of any? Okay. Okay, so why don't you think and tell me? So basically we are now checking if there exists a concave function, you know, which is discontinuous. Okay, that's what we are trying to check, right? Okay, so what do you think? Anybody? Okay. Okay, so let me tell you, you know, there is a result. So if you have an open interval or a real line, okay, if you have an open interval or a real line, then concavity implies continuity. So basically, concave function has to be continuous if it is on an open interval or real line. But if it is on a closed interval, I can give you discontinuous functions which are concave. But on open interval or real line, there is no way that you can find a concave function which is discontinuous. Okay, and I can just tell you in picture, why that is not true. Okay, so like for example, concave function. So let's just try and make concave function. Let's just try and do that, and let's just violate continuity at one point. Okay, I mean, let's just try and do that, and let's try and do that in multiple ways. We can try and violate continuity by violating right continuity, then left continuity. Let's try and do that, and let's see if we can show that the function is discontinuous. I mean, is not concave. Okay, I mean, let's just try and do that. Okay, so if I do something like this, okay, it's a concave function. Now what I'm going to do is, because it's defined on an open interval, so basically there are points to the right as well. Okay, so what I'm going to do is, let me just maybe drop the point. Let's just just make this particular point and just shift it up. Okay, so that it's just looks like concave. It's just that we violated continuity at one point. What do you think? Is this function concave still? It turns out that the answer is no. Earlier, while I was able to keep the line below it, now because of this point, I am not able to do it. Okay, because of this point, I'm not able to. Yes. Okay, let's just do that. Okay, so that's a good question. What if the discontinuity is below? Okay, will I be able to keep the entire graph below the function? Well, no, again, because if I take these 2 points, the entire line segment doesn't lie below the graph, because this one point is causing the problem. Is that fine? So basically, with concavity, continuity comes for free. Okay, provided it's an open interval. Okay, because if it's not an open interval, there is a possibility that you might have a concave function which is what, which is discontinuous. You can think of an example. Should I leave that as a homework? No, you want me to show you? Okay, how about this? So I kept the function concave in this entire interval 0 to 1. At 1, I'm going to just violate continuity. Now notice that what happened here. I was able to go to the right. Now what I'm going to do is, I'll make sure, because 1 is the end point, I don't have anywhere to go to the right. So my example is this. Now it works. Is that okay? Yes or no? So on closed interval 0, 1, you can have discontinuous concave functions. Now let's just check. No matter where you plot, to pick any 2 points on the graph, the line segment connecting them will lie below the graph or on the graph. Just check this for this particular function. Here the function is defined on closed interval 0, 1. In the first one, this one. Okay, in this one, I picked this point and connected them, and the line segment connecting them doesn't lie entirely below the graph. The reason is because if you see, this point lies below this line. Okay, and that's why the function is not concave. So if you violate continuity, concavity will be violated. What is, because concavity implies continuity if the function is on an open interval or real line. Okay, that's what we have actually shown through graphs, but it's not the proper proof. But yeah, I mean, that's something that you can actually see from here. Okay, so if the function is concave and defined on an open interval, if the function is concave and defined on an open interval, then it must be continuous. Okay, so what is the contrapositive of this? If the function is discontinuous, defined on an open interval, then it cannot be concave, right? So any discontinuous function cannot be concave, provided it is defined on real line on an open interval or on an open interval. Is that fine? Okay. And by the way, same holds for convexity. If a function is convex on an open interval or real line, then it must be continuous. Any discontinuous function defined on an open interval cannot be concave or convex. I mean, in fact, it's neither concave nor convex.